There's a place in space where galaxies go to die. It's called the Boötes Void, and it's a region of the universe roughly 330 million light-years across that contains almost nothing. In a typical volume of space this size, you would expect to find about 2,000 galaxies. The Boötes Void contains 60. Something happened there, something we don't understand, that emptied out a region of space larger than anything humans can properly conceptualize. This isn't the comforting universe you were taught about. This is a cosmos with holes in it, with structures so vast that light takes hundreds of millions of years to cross them, with forces we cannot see that pull galaxies apart and push the universe itself toward an ending we cannot prevent. You think you know about galaxies. You've seen pictures, spirals, ellipticals, pretty shapes glowing against the darkness. But those images are lies, not in content, but in scale. The Milky Way, our home galaxy, contains somewhere between 200 billion and 400 billion stars. The distance from one edge to the other is about 100,000 light-years. Light, travelling at 300,000 kilometers per second, takes 100,000 years to cross our galaxy. Let that settle in your mind. Our fastest spacecraft, Voyager 1, is travelling at about 17 kilometers per second relative to the Sun. At that speed, it would take roughly 1.7 billion years to cross the galaxy. Billion. With a B, humanity has existed for perhaps 300,000 years, civilization for maybe 10,000 years. The galaxy is so large that crossing it would take longer than complex life has existed on Earth. And the Milky Way is not special. It's a fairly average barred spiral galaxy. There are galaxies much larger. IC 1101, one of the largest known galaxies, has a diameter of about 6 million light-years. It contains roughly 100 trillion stars. 100 trillion. If you tried to count them, one per second, it would take you over 3 million years. But size isn't what makes galaxies disturbing. It's what they're made of. Visible matter, the stars and gas and dust that we can actually see, makes up only about 15% of a galaxy's mass. The rest is dark matter, a substance that doesn't interact with light, doesn't emit radiation, cannot be seen or touched or directly detected. We know it exists only because of its gravitational effects. This means that when you look at a galaxy, you're seeing less than a fifth of what's actually there. The rest is invisible, a dark scaffolding that shapes the structure but refuses to reveal itself. It's like looking at a building and seeing only some of the floors. The rest are there, holding up the visible parts, but they exist in a wavelength your eyes cannot perceive. Dark matter isn't evenly distributed. It forms halos around galaxies, extending far beyond the visible edges. The Milky Way is dark. Matter halo probably extends out to about 600,000 light-years, roughly 6 times the diameter of the visible galaxy. We're swimming in dark matter right now. It's passing through Earth, through your body, completely undetected except for its gravitational pull. Billions of dark matter particles are streaming through you every second. They don't interact with normal matter except through gravity. They pass through atoms like ghosts, through walls. You cannot feel them. You cannot stop them. They are fundamentally unknowable except through their effects on things we can see. What is dark matter made of? We don't know. The leading candidates are WIMPs, weakly interacting massive particles, hypothetical subatomic particles that have mass but don't interact electromagnetically. Despite decades of searching with increasingly sensitive detectors, we've never directly detected a WIMP. They remain theoretical. Alternative theories propose modified gravity, suggesting that our understanding of how gravity works on large scales is wrong. Maybe there is no dark matter, just equations that need correction. But modified gravity struggles to explain all the observations. Dark matter, despite being invisible and undetectable, fits the data better than changing the laws of physics. This is where we are as a species. We've mapped the cosmos, calculated the positions and motions of billions of galaxies, and discovered that 85% of the matter in the universe is something we cannot identify. We named it dark matter because we had to call it something, but the name admits our ignorance. It's dark because it doesn't emit light. It's matter because it has mass. Beyond that, we're guessing. Galaxies themselves are not static objects. They rotate, they merge, they evolve. Our Milky Way is currently cannibalizing several smaller galaxies. The Sagittarius dwarf elliptical galaxy is being torn apart by the Milky Way's gravity, its stars scattered into long streams that wrap around our galaxy like ribbons. This process has happened before. The Milky Way has consumed dozens of smaller galaxies over its lifetime, growing larger through cosmic cannibalism. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. This isn't a collision in the sense of two solid objects striking each other. Galaxies are mostly empty space. Stars are so far apart that even when galaxies merge, individual stellar collisions are rare. But the galaxies will pass through each other, their gravitational fields interacting, their structures distorted. The collision will take over 1 billion years. The two galaxies will approach, pass through each other, separate, and then fall back together again, multiple times. Each pass will further disrupt both galaxies. Stars will be flung out into intergalactic space. Gas clouds will collide, triggering massive bursts of star formation. The supermassive black holes at the centres of both galaxies will eventually merge, releasing gravitational waves that will ripple across the universe. The final result will be a single elliptical galaxy, larger than either predecessor, its spiral structure destroyed by the violence of the merger. This new galaxy, already nicknamed Milkomeda or Milkdromeda, will be home to the Sun, assuming it still exists. The night sky will be transformed, filled with unfamiliar constellations as stars from both galaxies mix. But this merger is local, almost intimate on cosmic scales. Andromeda is only 2.5 million light-years away, practically a neighbour. The universe is full of galaxies separated by tens, hundreds, millions of times that distance, and they're all moving. In 1929, Edwin Hubble made an observation that changed everything. He measured the light from distant galaxies and found that nearly all of them showed redshift. Their light stretched to longer wavelengths. The farther away a galaxy was, the more its light was redshifted. There was only one reasonable explanation. The galaxies were moving away from us, and the farther away they were, the faster they were receding. This was the discovery of cosmic expansion. The universe isn't static, it's growing, with space itself expanding, carrying galaxies apart like dots on an inflating balloon. This expansion isn't galaxies moving through space, it's space itself increasing, creating more distance between objects. The rate of expansion is described by the Hubble constant, currently measured at about 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, roughly 3.3 million light-years, a galaxy is receding from us at an additional 70 kilometers per second. A galaxy 10 megaparsecs away is receding at 700 kilometers per second. 100 megaparsecs away, 7,000 kilometers per second. At sufficient distances, galaxies are receding faster than the speed of light. This doesn't violate relativity because they're not moving through space faster than light. Space itself is expanding. There's no limit to how fast space can expand. The light speed limit applies to motion through space, not to the expansion of space itself. This creates a cosmic horizon. Galaxies beyond a certain distance are receding so fast that their light will never reach us. They exist, but they are fundamentally unobservable. They are beyond the edge of the observable universe, not because they're too faint or too far, but because the expansion of space prevents their light from ever arriving. The observable universe has a radius of about 46.5 billion light-years. This is larger than 13.8 billion light-years, the age of the universe times the speed of the light, because of expansion. The galaxies we see at the edge of the observable universe emitted their light 13.8 billion years ago, but they've been moving away from us the entire time that light was travelling. They're now 46.5 billion light-years away. Beyond that horizon, the universe continues. It might be infinite, it might be finite but unbounded, wrapping back on itself in ways we cannot visualize. We don't know. We can only observe the portion of the universe from which light has had time to reach us. Everything else is speculation, and it gets stranger. In 1998, observations of distant type Ia supernovae revealed something unexpected. The expansion of the universe isn't slowing down under the influence of gravity, as everyone assumed it would be. It's accelerating. Galaxies are moving apart faster and faster over time. This should not happen. Gravity attracts. It pulls things together. The expansion of the universe should be decelerating, slowed by the gravitational attraction of all the matter it contains. But it's not. Something is pushing the universe apart, overcoming gravity, accelerating the expansion. We call this dark energy. Like dark matter, the name is an admission of ignorance. We don't know what it is. We don't know why it exists. We just know it's there because we can measure its effects. And it's not a small effect. Dark energy makes up about 68% of the total energy content of the universe. Think about that. Ordinary matter, the stuff that makes up stars, planets, and people, is about 5% of the universe. Dark matter is about 27%. Dark energy is 68%. 95% of the universe is made of things we cannot identify. We've named them, measured their effects, incorporated them into our models, but we don't know what they are. The leading explanation for dark energy is the cosmological constant, a property of space itself. In this model, empty space has energy. The vacuum isn't empty but seethes with quantum fluctuations, particles and antiparticles briefly popping into existence and annihilating. This vacuum energy creates a repulsive gravitational effect that pushes space apart. The problem is that when you calculate what the vacuum energy should be based on quantum field theory, you get a number that's about 10 to the power of 120 times larger than what we observe. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in physics. Our best theories predict a value for dark energy that's wrong by 120 orders of magnitude. Alternative theories propose that dark energy isn't constant but varies over time, or that it's a new field pervading space, or that our understanding of gravity on cosmic scales is fundamentally wrong. We don't know. We're throwing ideas at the problem and seeing what sticks. What we do know is that dark energy's effects have changed over cosmic history. In the early universe, when matter was denser, gravity dominated. The expansion was decelerating, but as the universe expanded and matter spread out, its gravitational influence weakened. About 6 billion years ago, dark energy became dominant, and the expansion began to accelerate. This acceleration has profound implications for the universe's future. If dark energy remains constant, the expansion will continue accelerating forever. Galaxies beyond our local group will eventually recede so fast that they disappear beyond the cosmic horizon. The observable universe will shrink, not in actual size, but in content, as more and more galaxies slip away. In the far future, observers in the Milky Way, assuming any exist, will see a very different universe. The local group, Milky Way, Andromeda, and a few dozen smaller galaxies will have merged into a single large galaxy. Beyond that, darkness. No distant galaxies, no cosmic microwave background, no evidence that the universe extends beyond the local group. Future astronomers, if they exist, might conclude that the universe is just their galaxy surrounded by infinite empty space. They would be wrong, but they would have no way to know. The evidence of cosmic expansion, of the Big Bang, of the larger universe, will have disappeared, carried away by accelerating expansion. We're living in a special time, cosmologically speaking. We can still see the distant universe. We can still detect the cosmic microwave background. We can still measure cosmic expansion and deduce the Big Bang. In the deep future, This won't be possible. The universe will have expanded so much that evidence of its own history will be erased. This is called the information horizon problem. Information about the early universe is gradually being pushed beyond the cosmic horizon, becoming forever inaccessible. We're in a narrow window of cosmic time when intelligent observers can deduce the universe's origin and evolution. Before this window, life hadn't evolved. After this window, the evidence will be gone. Galaxies come in different types, and the distribution isn't random. Edwin Hubble classified them into a sequence: ellipticals, lenticulars, spirals, and irregulars. He arranged them in a tuning fork diagram, with ellipticals on the handle and spirals and barred spirals on the tines. Elliptical galaxies are smooth, featureless, containing mostly old stars and little gas or dust. They range from nearly spherical to highly elongated. The largest galaxies in the universe are giant ellipticals, found at the centres of galaxy clusters. These are often formed through mergers, multiple galaxies colliding and combining into a single massive object. Spiral galaxies have distinct structures: a central bulge, a flat disk with spiral arms, and a surrounding halo. The spiral arms are regions of active star formation, glowing with young, hot blue stars. The bulge contains older, redder stars. Our Milky Way is a barred spiral with a central bar-shaped structure from which the spiral arms extend. The spiral structure isn't permanent. The arms aren't fixed collections of stars. They're density waves, regions where stars and gas temporarily bunch up, like traffic jams on a highway. Stars move in and out of the arms as they orbit the galactic centre. The arms persist because the density wave rotates at a different speed than the stars. Irregular galaxies lack clear structure. They're chaotic, often the result of gravitational interactions with other galaxies. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, are irregulars. They've been distorted by tidal forces from the Milky Way's gravity. But galaxy classification is more complex than Hubble's simple scheme suggests. There are ring galaxies, polar ring galaxies, galaxies with multiple nuclei, galaxies with active star formation in their centres, galaxies with quiescent cores. The diversity is immense, and at the centres of most large galaxies there's something lurking, something massive, something dark. Supermassive black holes. Nearly every large galaxy has a supermassive black hole at its centre. These are not stellar mass black holes formed from collapsing stars. They're millions to billions of times more massive than the Sun. The one at the centre of the Milky Way, Sagittarius A star, contains about 4 million solar masses. The one at the centre of the giant elliptical galaxy M87 contains about 6.5 billion solar masses. How these monsters form is still debated. They might grow from smaller seed black holes through accretion and mergers. They might form directly from the collapse of massive gas clouds in the early universe. They might be remnants of the very first generation of stars. We don't know. What we do know is that they shape galactic evolution. The mass of a galaxy's central black hole is tightly correlated with the mass of its bulge and with the velocity dispersion of stars in the galaxy. This suggests a feedback mechanism where the black hole's growth affects the galaxy, and the galaxy's evolution affects the black hole. When a supermassive black hole actively accretes matter, it becomes an active galactic nucleus, one of the most luminous objects in the universe. Matter falling into the black hole forms an accretion disk, heated to millions of degrees by friction. The disk emits radiation across the electromagnetic spectrum, from radio waves to gamma rays. Some active galactic nuclei produce jets, narrow beams of particles accelerated to nearly the speed of light and shot out perpendicular to the accretion disk. These jets can extend for millions of light years, far beyond the galaxy itself, pumping energy into intergalactic space. Quasars are the most extreme active galactic nuclei. These are supermassive black holes feeding so rapidly that they outshine their entire host galaxies. The brightest quasars can be more than 1,000 times more luminous than the Milky Way, all that energy coming from a region smaller than our solar system. The quasar 3C273 was one of the first identified. It appears as a star in optical telescopes, but its spectrum revealed something extraordinary. The emission lines were redshifted by about 16%, placing it roughly 2.4 billion light-years away. For an object that distant to be visible at all, it had to be incredibly luminous. We now know that quasars were far more common in the early universe. Looking at distant galaxies, looking back in time because of light's finite speed, we see many more quasars than exist nearby. This suggests that supermassive black holes were more active when the universe was younger, perhaps because there was more gas available to fuel them. As galaxies age, they consume or expel their gas. Star formation slows. The central black hole runs out of material to accrete. The galaxy becomes quiescent, its black hole dormant. The Milky Way's central black hole is relatively quiet now, accreting only small amounts of material. But observations suggest it was more active in the past, and could become active again if enough gas falls in. In 2019, the Event Horizon Telescope captured an image of the supermassive black hole at the centre of M87. The image shows a bright ring of emission surrounding a dark centre, the black hole's shadow. This shadow is the event horizon and the region around it where light is so strongly bent by gravity that it cannot escape. The M87 black hole is massive enough that its event horizon has a diameter of about 38 billion kilometres, roughly 250 times the distance from Earth to the Sun. It's rotating, dragging space-time around with it, and it's launching a jet visible across thousands of light-years. In 2022, they released an image of Sagittarius A star, our own galactic centre black hole. It's much smaller, about 52 times the Sun-Earth distance across, but closer and therefore appears similar in size on the sky. The image confirms the presence of the event horizon and matches predictions from general relativity with remarkable precision. These images are triumphs of observational astronomy and theoretical physics. They show that Einstein's equations, written over a century ago, accurately describe objects at extremes of gravity where space-time itself is warped beyond recognition. But black holes are just one component of galaxies. The distribution of galaxies themselves reveals larger structures. Galaxies aren't scattered randomly through space. They cluster, forming groups, clusters, and superclusters connected by filaments of dark matter and gas. The Milky Way is part of the Local Group, a collection of about 80 galaxies dominated by the Milky Way and Andromeda. The Local Group is about 10 million light-years across. Most of its members are dwarf galaxies, small irregular or elliptical galaxies containing millions to billions of stars. The Local Group is itself part of the Virgo supercluster, a larger structure containing about 100 galaxy groups and clusters spanning about 110 million light-years. At the centre of this supercluster is the Virgo cluster, containing about 1,500 galaxies dominated by the giant elliptical M87. But even superclusters aren't the largest structures. Observations reveal a cosmic web, a network of filaments and voids extending across the observable universe. Galaxy superclusters are strung along the filaments like beads on strings. Between the filaments are vast voids, regions of space containing very few galaxies. The largest known structure is the Hercules Corona Borealis Great Wall, a galactic filament about 10 billion light-years long. It's so large that it challenges cosmological models. According to the cosmological principle, the universe should be roughly uniform on large scales. Structures this large shouldn't exist, yet they do. The cosmic web formed through gravitational instability. In the early universe, matter was distributed almost uniformly, with tiny density fluctuations of about 1 part in 100,000. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter, becoming denser still. Less dense regions lost matter, becoming voids. Dark matter played a crucial role. Because it doesn't interact electromagnetically, it could collapse without being heated or dispersed by radiation pressure. Dark matter formed the scaffolding first, and normal matter fell into the gravitational wells it created. Stars and galaxies formed where dark matter was densest. This process is called hierarchical structure formation. Small structures formed first, then merged to create larger ones. Dwarf galaxies merged into larger galaxies. Galaxies clustered into groups. Groups merged into clusters. Clusters connected into superclusters and filaments. Computer simulations of structure formation, incorporating dark matter and dark energy, reproduce the cosmic web we observe. The simulations start with initial conditions from the early universe and evolve them forward in time using the laws of gravity. The result matches the distribution of galaxies we see, providing strong evidence that our understanding of cosmic evolution is broadly correct. But there are anomalies. Some galaxies are too massive to have formed so early. Some galaxy clusters are more structured than simulations predict. The James Webb Space Telescope has discovered galaxies at extremely high redshifts, existing when the universe was only a few 100 million years old, that appear more evolved than expected. These observations might require adjustments to our models, or they might indicate gaps in our understanding of how galaxies form and evolve. Astronomy is always on the edge between what we know and what we're discovering. Every new observation has the potential to confirm or challenge our theories. Galaxy clusters are extraordinary objects in their own right. The Coma cluster contains over 1,000 galaxies in a region about 20 million light-years across. The combined mass is about 10 to the 15th solar masses, 10 quadrillion times the mass of the Sun. Most of this mass is dark matter. The galaxies themselves are only a small fraction of the total. Between the galaxies and clusters is hot gas, heated to tens of millions of degrees by gravitational compression as it falls into the cluster's potential well. This intracluster medium emits X-rays, making galaxy clusters some of the brightest X-ray sources in the sky. The gas contains more mass than all the galaxies in the cluster combined, though still less than the dark matter. Galaxy clusters are held together by gravity, but they're also the sites of intense activity. Galaxies within clusters move at speeds of hundreds to thousands of kilometers per second. They interact, merge, and sometimes collide. These interactions can strip gas from galaxies, quenching star formation. The Bullet cluster is a famous example of two galaxy clusters that collided. Observations show that the hot gas, visible in X-rays, stayed behind during the collision, slowed by electromagnetic interactions. But the galaxies and the dark matter pass through relatively unimpeded. Gravitational lensing measurements show that most of the mass is in the dark matter, which passed through the collision and is now separated from the visible gas. This observation is powerful evidence for dark matter's existence. The mass distribution doesn't match the visible matter distribution. There's additional mass that doesn't interact electromagnetically, exactly as dark matter theories predict. Alternative theories like modified gravity struggle to explain the Bullet cluster. Gravitational lensing is one of our most important tools for studying dark matter. When light passes near a massive object, its path is bent by the object's gravity. This is a prediction of general relativity, confirmed by observations during the solar eclipse of 1919 when stars appeared to shift position as their light passed near the Sun. On larger scales, galaxies and galaxy clusters act as gravitational lenses. Light from background galaxies is bent as it passes through the foreground cluster's gravitational field. The result can be multiple images of the same background galaxy, arcs of light, or even complete rings called Einstein rings. By measuring the distortion of background galaxies, we can map the distribution of mass in the foreground cluster, including the dark matter. These maps reveal that dark matter dominates the mass budget, and that its distribution doesn't match the distribution of visible matter. The dark matter is more extended, forming halos around and between galaxies. Weak gravitational lensing measures subtle distortions across large areas of sky, revealing the cosmic web structure. By analysing the shapes of millions of galaxies, we can map how dark matter is distributed across the universe. These maps confirm the filamentary structure predicted by simulations and provide constraints on dark matter's properties. The study of large-scale structure also reveals cosmic flows. Galaxies aren't just moving due to cosmic expansion. They also have peculiar velocities, motion relative to the Hubble flow caused by gravitational attraction to nearby mass concentrations. The local group is falling toward the Virgo cluster at about 200 kilometers per second. The Virgo cluster itself is moving toward a larger mass concentration called the Great Attractor, located about 250 million light-years away in the direction of the constellations Hydra and Centaurus. The Great Attractor is hidden behind the plane of the Milky Way, where dust and stars block our view of the distant universe. But we can infer its presence from the motion of galaxies around it. It's a region of space containing tens of thousands of galaxies with a total mass of tens of quadrillions of solar masses. But even the Great Attractor is being pulled by something larger. The Shapley supercluster, about 650 million light-years away, is one of the most massive structures known, containing over 8,000 galaxies. Its gravitational pull affects a vast region of space, drawing galaxy clusters toward it. These cosmic flows reveal the universe's mass distribution on the larger scales. By mapping how galaxies move, we can infer where mass is concentrated, even if we can't see it directly. This provides another way to study dark matter and dark energy, complementing direct observations. The cosmic microwave background is our earliest snapshot of the universe, light from about 380,000 years after the Big Bang. At that time, the universe had cooled enough for neutral atoms to form, allowing light to travel freely for the first time. This light has been travelling through space ever since, stretched by cosmic expansion from visible wavelengths to microwaves. The CMB is remarkably uniform, with a temperature of about 2.7 Kelvin across the entire sky. But there are tiny fluctuations, variations of about 1 part in 100,000. These fluctuations are the seeds of all structure in the universe. Regions that were slightly denser became the cores of galaxy superclusters. Slightly less dense regions became voids. The pattern of CMB fluctuations encodes information about the universe's composition, age, and geometry. Detailed measurements by satellites like COBE, DOMMAP, and Planck have determined cosmic parameters with remarkable precision. We know the universe is 13.8 billion years old, that it's spatially flat to within measurement error, and that it contains the proportions of dark matter, dark energy, and ordinary matter mentioned earlier. The CMB also reveals something subtle but profound. The universe is expanding uniformly in all directions. The CMB looks the same, no matter where we look, aside from tiny fluctuations and a small dipole caused by our motion relative to the CMB rest frame. This uniformity is called isotropy. But there's a problem. Regions of the CMB on opposite sides of the sky are separated by about 90 billion light-years, given expansion. Light from one side has not had time to reach the other side. They've never been in causal contact. They couldn't have influenced each other or exchanged information, yet they have the same temperature to 1 part in 100,000. How did widely separated regions of the universe coordinate to have nearly identical properties if they've never interacted? This is called the horizon problem, and the solution is inflation. According to inflationary theory, the universe underwent a brief period of exponential expansion in its first fraction of a second. During this inflationary epoch, a region small enough to have reached thermal equilibrium expanded to become larger than the observable universe. After inflation ended, the universe continued expanding at a slower rate. The regions we see today in opposite directions of the sky were once close together, in causal contact, able to reach the same temperature. Then inflation stretched them apart faster than light. placing them beyond each other's horizons. Inflation solves several cosmological problems. It explains the uniformity of the CMB, it explains why the universe is so flat, and it predicts the pattern of fluctuations we observe in the CMB. Tiny quantum fluctuations during inflation were stretched to cosmic scales, seeding the structure we see today. Inflation is a compelling theory, but it raises questions. What drove inflation? What turned it off? Did it happen everywhere simultaneously, or are there regions where inflation never ended, creating a multiverse of pocket universes? These questions push the boundaries of physics into speculative territory. The formation of the first stars and galaxies, the epoch of rhyonisation, occurred when the universe was a few 100 million years old. Before this, the universe was dark. After the Big Bang recombination that produced the CMB, there were no stars yet. The universe entered a period called the Dark Ages, where the only light was the cooling CMB. Eventually, the first stars formed from primordial hydrogen and helium. These population 3 stars were massive, hot, and short-lived. Their radiation ionized the surrounding gas, creating bubbles of ionized hydrogen that grew and merged. This is the epoch of reionization, when the universe transitioned from neutral to ionized. The James Webb Space Telescope is designed to observe this era, looking for the first galaxies and studying how they reionize the universe. Early results show galaxies existing earlier and appearing more evolved than expected, challenging our understanding of how quickly structure could form. One surprising discovery is the abundance of massive galaxies at high redshift. Some appear to contain billions of solar masses when the universe was less than 1 billion years old. Standard models struggle to explain how so much mass could assemble so quickly. Either our models need adjustment, or these observations are revealing new physics about the early universe. The evolution of galaxies over cosmic time reveals a universe in constant transformation. Early galaxies were smaller, more irregular, often engaged in violent mergers. They formed stars at prodigious rates, converting gas into stellar populations far faster than galaxies do today. The peak of cosmic star formation occurred when the universe was about 3 to 4 billion years old. During this epoch, galaxies were forming stars at rates 10 to 100 times higher than the Milky Way's current rate. The universe was brighter, more active, more chaotic than it is now. Since then, star formation has declined. Galaxies have consumed or expelled much of their gas. Mergers have built larger galaxies but also disrupted the conditions needed for efficient star formation. The universe is aging, settling into a more quiescent state. This cosmic downturn in star formation has profound implications. Most stars that will ever exist have already formed. The universe has passed its peak of stellar production and is now in a long decline. In the far future, when the last molecular clouds have been consumed, star formation will cease entirely. The fate of individual galaxies depends on their environment. Isolated galaxies like the Milky Way can continue forming stars slowly for billions of years, gradually converting their remaining gas into stellar populations. But galaxies in dense clusters experience different fates. Ram pressure stripping occurs when a galaxy moves through the hot intracluster medium. The pressure from this tenuous gas is enough to strip gas from the galaxy, especially from its outer regions. Without gas, star formation ceases. The galaxy becomes red and dead, its stellar population aging without replacement. Harassment involves repeated high-speed encounters between galaxies in a cluster. Each encounter perturbs the galaxy's structures, heating their stellar populations and removing gas. Over many encounters, spiral galaxies can be transformed into ellipticals through harassment. Strangulation is a gentler process. When a galaxy falls into a cluster, the hot intracluster medium strips away its extended gas halo. The galaxy retains the gas in its disk initially, but without replenishment from the halo, star formation gradually declines as the disk gas is consumed. The galaxy slowly fades from blue to red over billions of years, These environmental processes explain why galaxy clusters contain mostly elliptical and lenticular galaxies, while isolated galaxies are often spirals. The cluster environment is hostile to spiral structure and active star formation, but not all galaxies are passive victims of their environment. Some are monsters, actively consuming everything around them. Brightest cluster galaxies are the massive ellipticals found at the centres of galaxy clusters. They grow through cannibalism, consuming smaller galaxies that wander too close. These BCGs can contain trillions of solar masses. Their stellar halos extend for millions of light years. They often have multiple nuclei, the remnants of galaxies they've absorbed. And at their centres lie some of the most massive black holes in the universe, billions to tens of billions of solar masses. The black hole at the centre of the Phoenix Cluster BCG contains about 20 billion solar masses. It's accreting matter at extraordinary rates, making the galaxy's core one of the most luminous objects known. The energy output is so intense that it heats the surrounding intracluster medium, preventing it from cooling and forming stars. This is an example of active galactic nucleus feedback. The black hole's energy output regulates star formation not just in its host galaxy, but across the entire cluster. Without this feedback, the hot gas would cool, fall into galaxies, and form stars at unsustainable rates. The black hole acts as a thermostat, maintaining equilibrium. The relationship between black holes and their host galaxies is one of the most important discoveries in modern astronomy. The mass of a galaxy's central black hole correlates tightly with the mass of its bulge and with the velocity dispersion of stars in the galaxy. This suggests they evolve together, each influencing the other. How this relationship forms is still debated. Does the black hole grow first and then limit the galaxy's growth through feedback? Does the galaxy form first and feed the black hole? Or do they grow simultaneously through processes that naturally link their masses? All three scenarios probably occur under different conditions. What's clear is that supermassive black holes play a critical role in galaxy evolution. They regulate star formation through feedback. They drive powerful outflows that enrich the intergalactic medium with metals. They produce jets that can extend across millions of light years. Ignoring black holes gives an incomplete picture of how galaxies work. The intergalactic medium itself is not empty. Between galaxies lies diffuse gas, heated to millions of degrees in galaxy clusters, but cooler and more tenuous in the cosmic web's filaments. This warm-hot intergalactic medium contains a significant fraction of the universe's normal matter. For decades, astronomers faced a problem. Observations of the local universe showed less ordinary matter than cosmological models, predicted based on the CMB. But half the baryons, the normal matter made of protons and neutrons, were missing. They weren't in stars, weren't in cold gas, weren't in the hot intracluster medium. Where were they? The answer appears to be in the warm-hot intergalactic medium, along filaments of the cosmic web. This gas is too hot to emit visible light, but too cool to emit strong X-rays. It exists at temperatures of 100,000 to 10 million Kelvin, in a regime difficult to observe. Recent observations, particularly in the ultraviolet and X-ray, have detected this missing baryonic matter. The cosmic web's filaments are not just dark matter scaffolding, but also contain hot gas, heated by gravitational compression and shocks as it falls into the large-scale structure. This gas is enriched with heavy elements, metals produced in stars and distributed by supernovae and galactic winds. Even intergalactic space, vast and empty as it seems, contains the products of stellar nucleosynthesis. The entire universe has been polluted, in the technical sense, by generations of stars. The metallicity of intergalactic gas increases over cosmic time as more stars form and die, enriching their surroundings. In the early universe, the intergalactic medium was pristine, containing only hydrogen and helium from the Big Bang. Now it contains small but measurable amounts of carbon, oxygen, silicon, iron, and other elements. Studying the intergalactic medium requires looking through it, observing how it absorbs light from distant quasars. Each gas cloud along the line of sight creates absorption lines in the quasar spectrum. By analysing these lines, we can determine the cloud's composition, temperature, density, and velocity. The Lyman alpha forest is a series of absorption lines seen in quasar spectra, created by neutral hydrogen in the intergalactic medium. Each line corresponds to a different gas cloud at a different redshift. The forest becomes denser at higher redshifts, corresponding to earlier cosmic times when the universe was smaller and denser. By studying the Lyman alpha forest, we can trace the distribution of matter in the early universe, even the dark matter, because the gas follows the dark matter's gravitational potential. This provides a probe of structure, formation complementary to observations of galaxies themselves. The universe's large-scale structure is not static. It continues to evolve under gravity's influence. Simulations predict that in the far future, dark energy will dominate even more completely. The expansion will accelerate to the point where structures cannot grow. Eventually, even galaxy clusters will be torn apart as the space between them expands faster than their gravity can hold them together. This is the Big Rip scenario, one possible ultimate fate of the universe if dark energy's strength increases over time. In this scenario, the acceleration becomes so extreme that bound structures are progressively destroyed. First galaxy clusters dissolve, then galaxies, then solar systems, then planets, and finally atoms. Themselves are torn apart as space expands faster than the forces holding them together. Current observations suggest dark energy's density is constant, which would lead not to a big rip but to a gentler heat death. The expansion continues accelerating, but bound structures remain bound. The universe simply becomes increasingly empty and dark as galaxies recede beyond each other's horizons. Another possible fate is the Big Crunch. If dark energy weakens or reverses, gravity could eventually halt the expansion and reverse it. The universe would begin contracting, galaxies would blue shift instead of red shift, and eventually everything would collapse back into a hot, dense state similar to the Big Bang. A variant is the Big Bounce, where the universe cycles through expansions and contractions infinitely. Each big crunch is followed by a new Big Bang, creating a cyclic universe. This is speculative and faces theoretical challenges, but it remains a possibility. The accelerating expansion creates a crisis for cosmology. If the expansion continues accelerating, the distant future will be very different from today. Observers in the far future will see only their local galaxy group, surrounded by darkness. The cosmic microwave background will have redshifted beyond detectability. Distant galaxies will have disappeared beyond the horizon. These future observers will have no evidence that the universe is larger than their local group. They will have no way to discover cosmic expansion, no way to deduce the Big Bang, no way to measure dark energy. The universe's history will be hidden from them. We live in a privileged time when the universe's history is still observable. This cosmic coincidence, that intelligent life arose when evidence of cosmic origins is still accessible, has led some to invoke anthropic reasoning. Perhaps the conditions that allow the universe's history to be observable are somehow necessary for intelligent life to exist. This reasoning is controversial, is difficult to test and easy to abuse, but it does highlight a genuine puzzle. We happen to evolve at a time when the universe's secrets are still visible, a few trillion years from now. That won't be true. The study of cosmology reveals a universe stranger than our ancestors imagined. Not a static cosmos with Earth at the centre, but an expanding universe billions of light years across, filled with billions of galaxies, each containing billions of stars, most of which have planets. And most of this universe is invisible. Dark matter outweighs visible matter by 5 to 1. Dark energy outweighs all matter, dark and visible, by more than 2 to 1. We're made of the minority component, the 5% of the universe that interacts with light. This is humbling. Not only are we not at the centre of the universe, We're not even made of the dominant type of matter. We're exotic in the literal sense. Most of the universe is something else, something we cannot directly perceive. Yet we can study it. Through careful observation and clever reasoning, we've deduced the existence of dark matter and dark energy. We've measured their properties and traced their effects. We've incorporated them into models that successfully predict the universe's behaviour. This is the power of science. We're not limited to direct perception. We can infer the existence of things we cannot see by observing their effects on things we can see. Dark matter bends light, affects rotation curves, influences structure formation. Dark energy accelerates expansion. These effects are measurable, even if the underlying causes remain mysterious. The next generation of telescopes and surveys will refine our understanding. The Vera Rubin Observatory will survey the entire visible sky repeatedly, tracking how billions of galaxies change over time. The Nancy Grace Roman Space Telescope will map dark matter distribution through gravitational lensing. The European Space Agency's Euclid mission will measure galaxy positions and shapes to constrain dark energy's properties. Future gravitational wave detectors will observe black hole mergers across cosmic time, tracing how black holes grow and galaxies evolve. Neutrino observatories will detect neutrinos from distant astrophysical sources, providing a new window on high-energy processes. Radio arrays will map neutral hydrogen across the universe, revealing gas distributions and cosmic structure. Each new instrument extends our reach, revealing previously hidden aspects of the cosmos. The history of astronomy is a history of expanding awareness. From naked-eye observations to optical telescopes to space-based observatories operating across the electromagnetic spectrum, each advance has revealed new phenomena. We've discovered that the universe is expanding, that it began in a big bang, that it contains dark matter and dark energy, that supermassive black holes lurk at galactic centres, that planets are common, that the fundamental constants appear fine-tuned for complexity. These discoveries raise new questions. Why did the universe begin? Why does it have the properties it does? Are the fundamental constants really fine-tuned? And if so, why? Is our universe unique? Or is it one of many in a multiverse? Can we ever answer these questions? Or are some forever beyond our reach? Philosophy and physics blur at these boundaries. We're asking questions about existence itself, about why there's something rather than nothing, about whether the universe requires explanation or simply is. Some find these questions disturbing. The universe's indifference to human concerns, its vast scales, its fundamental inscrutability in matters of ultimate origin and fate, all this can provoke existential anxiety. We're small, brief, and made of the universe's least common type of matter. But there's another perspective. We're part of the universe observing itself. The atoms in our bodies were forged in stars. The energy powering our thoughts comes ultimately from fusion reactions in the sun. We're intimately connected to the cosmos, not separate observers but participants, and we can understand it, at least partially. The laws of physics apply everywhere. The same gravity that holds us to Earth governs galaxy clusters. The same quantum mechanics that determines atomic structure operates in stellar cores. The universe is comprehensible. This comprehensibility is perhaps the deepest mystery. Why should the universe be such that intelligent observers can arise and understand it? Why should mathematics, a product of human minds, describe physical reality so perfectly? Why do the laws of physics appear simple and elegant rather than arbitrary and complex? These questions might not have answers, or the answers might lie in directions we haven't yet explored. Perhaps the multiverse idea is correct, and we observe a comprehensible universe because only comprehensible universes can produce observers. Perhaps there's a deeper theory waiting to be discovered that explains why the laws must be as they are. Or perhaps the universe simply is, without ultimate explanation, and the search for final answers is misguided. Perhaps there are questions that cannot be answered, limits to knowledge that cannot be transcended. The cosmic web stretches across the observable universe, a network of filaments and nodes that reveals the large-scale organization of matter. From our position in the Milky Way, we can trace these structures outward, mapping how galaxies cluster and how voids separate them. The local sheet is a flattened concentration of galaxies that includes the local group. It's part of a larger structure, a wall of galaxies extending across hundreds of millions of light-years. These walls surround voids, creating a foam-like structure when viewed on the larger scales. The Sloan Great Wall is one such structure, a vast concentration of galaxies about 1.4 billion light-years long. It was discovered through the Sloan Digital Sky Survey, which mapped the positions of millions of galaxies. The wall isn't a solid object, but a connected filament of galaxy, superclusters. When you map enough galaxies, patterns emerge. The distribution isn't random. Galaxies trace out the underlying dark matter distribution, which collapsed first and provided the gravitational wells into which normal matter fell. The cosmic web is dark matter's architecture made visible through the galaxies that formed within it. Simulations of cosmic structure formation begin with the initial density fluctuations from the early universe. Tiny quantum variations stretch to cosmic scales by inflation. These fluctuations are seeded into the simulation as initial conditions. Then gravity takes over, amplified by dark matter's presence. Over billions of simulated years, the structure evolves. Dense regions attract more matter and become denser. Underdense regions lose matter and become voids. Filaments form as matter streams along the paths of least resistance in the gravitational potential. At the intersections of filaments, massive galaxy clusters accumulate. The final result, after 13.8 billion years of simulated evolution, looks remarkably like the real universe. The statistics match. The distribution of void sizes, filament lengths, cluster masses all correspond to observations. This concordance between simulation and reality validates our understanding of cosmic structure formation. But simulations also make predictions beyond what we've observed. They show that the cosmic web extends beyond the observable universe. The filaments and voids continue in all directions, limited only by the finite size of the simulation volume. If the universe is infinite, then the cosmic web is infinite, an endless network of structure extending forever. This raises questions about what lies beyond our cosmic horizon. If the universe extends infinitely, then every possible arrangement of matter exists somewhere, repeated infinitely many times. There would be infinite copies of you, infinite variants differing in small details, infinite Earths, infinite Milky Ways. This seems absurd, but it's a consequence of infinity combined with finite information content in any given volume. If space is infinite and matter is arranged in all possible ways, then repetition is inevitable. You're not unique in an infinite universe. You're replicated endlessly. This assumes the universe is infinite, which we don't know. Observations show the universe is flat to within measurement precision, which suggests infinite extent if exactly flat. But slight curvature could make it finite, wrapped back on itself in ways we cannot easily visualize. A finite universe could be closed like the surface of a sphere, unbounded but finite in volume. Travel far enough in one direction, and you'd eventually return to your starting point from the opposite direction. Light could potentially circle the universe, creating ghost images of galaxies at different apparent distances. Current observations don't show evidence of such wrapping. The observable universe appears consistent with being an infinite flat space, or a finite space much larger than the observable region. We cannot see beyond the cosmic horizon, so we cannot definitively determine the universe's global topology. These questions about the universe's size and shape connect to deeper questions about its origin. The Big Bang theory describes how the universe evolved from a hot, dense state, but it doesn't explain why that state existed or what came before. Some cosmologists propose that the Big Bang wasn't the beginning but a transition, preceded by a previous state. Perhaps the universe contracted from a previous cycle, bounced, and began expanding again. Perhaps it emerged from a quantum fluctuation in a pre-existing space. Perhaps time itself began at the Big Bang, making the question of what came before meaningless. General relativity predicts a singularity at the Big Bang, a point of infinite density and curvature where the equations break down. This is similar to the singularity at the centre of a black hole. Just as we don't know what happens at a black hole singularity, we don't know what happened at the Big Bang singularity. Quantum gravity, a theory combining general relativity and quantum mechanics, should resolve these singularities, but we don't have a complete theory of quantum gravity yet. String theory and loop quantum gravity are leading candidates, but neither is fully developed or tested against observation. In the absence of a complete theory, we can speculate. Perhaps the singularity is smoothed out by quantum effects. Perhaps the universe tunneled from nothing through quantum processes. Perhaps it's eternal, with no true beginning. These ideas exist at the boundary between physics and philosophy. The cosmic microwave background provides our earliest observable snapshot of the universe, but it's not the earliest moment. Before recombination, the universe was opaque to light. Photons scattered constantly off free electrons, unable to travel far. We cannot see directly to earlier times using light, but we can potentially observe earlier eras using gravitational waves or neutrinos, which interact weakly with matter and could propagate freely even in the early universe. A gravitational wave background from the Big Bang, if detected, would provide information about the universe's first moments. Inflation should have produced gravitational waves, ripples in space-time generated by the rapid expansion. These primordial gravitational waves would have left an imprint on the CMB, a specific pattern in the polarization of the microwave background. Detecting this signature would confirm inflation and provide details about how it occurred. Experiments like BICEP, Keck Array and others are searching for this signal. In 2014, the BICEP-2 collaboration announced a detection, but subsequent analysis showed the signal was likely from dust in our galaxy, rather than primordial gravitational waves. The search continues. The early universe was a simpler place than today. At the highest energies shortly after the Big Bang, the fundamental forces might have been unified. As the universe cooled, symmetries broke and forces separated. First gravity, then the strong nuclear force, then the electromagnetic and weak forces split. This process of symmetry breaking shaped the universe's properties. The relative strengths of the fundamental forces, the masses of elementary particles, the nature of dark matter, all were determined by phase transitions in the early universe as it cooled from the initial high-energy state. Understanding these phase transitions requires particle physics and cosmology to work together. The Large Hadron Collider recreates high-energy conditions similar to the early universe, allowing physicists to study particle behavior under extreme conditions. Cosmological observations constrain what must have happened based on the universe we see today. This interplay between the very large and the very small, between cosmology and particle physics, is one of the most productive areas in modern science. The universe's evolution depends on particle physics. The properties of elementary particles are constrained by cosmological observations. Neither field can fully understand its domain without the other. Dark matter's identity remains one of the biggest unsolved problems. If it's composed of WIMPs, we should be able to detect them. These particles should occasionally interact with normal matter, despite being weakly interacting. Ultra-sensitive detectors deep underground are searching for these rare interactions. So far, no confirmed detection. The lack of signal is starting to constrain WIMP properties, ruling out some of the parameter space. Either WIMPs interact even more weakly than expected, or dark matter is something else entirely. Axions are another candidate. Hypothetical particles much lighter than WIMPs. They would have been produced abundantly in the early universe and could make up the dark matter. Experiments are searching for axions by looking for their conversion to photons in strong magnetic fields. Primordial black holes, formed in the early universe from density fluctuations, are another possibility. These wouldn't be the black holes formed from stellar collapse, but much smaller objects, potentially ranging from microscopic to many solar masses. They would be dark, have mass, and interact only through gravity, fitting dark matter's properties. Recent observations of gravitational waves from merging black holes have revived interest in primordial black holes. Some of the detected black holes have properties that might be difficult to explain through stellar evolution, but could make sense if they formed in the early universe. Or dark matter might be something we haven't thought of yet, a particle or phenomenon outside the standard model of particle physics that we'll only discover through persistent observation and experimentation. Dark energy is even more mysterious. At least dark matter behaves like matter, clumping gravitationally. Dark energy is smooth, distributed uniformly throughout space, and causes accelerated expansion. Its nature is completely unknown. The cosmological constant, Einstein's mathematical term representing vacuum energy, fits observations. But the value required is so much smaller than quantum field theory predicts that it seems like a conspiracy. Why is vacuum energy almost but not quite zero? Some physicists invoke anthropic reasoning. In a multiverse with varying vacuum energy, only universes with values close to what we observe could develop structure and life. We observe this value because if it were much larger, galaxies wouldn't form. If it were negative, the universe would have recollapsed. This reasoning is unsatisfying to many. It replaces why is the cosmological constant this value with why does the multiverse exist and have varying constants? It pushes the question back rather than answering it. Alternative explanations propose that dark energy is dynamic, a field that varies over time and space. This is called quintessence. Unlike the cosmological constant, quintessence could evolve, potentially explaining why dark energy dominates now rather than earlier in cosmic history. Testing these ideas requires precise measurements of how dark energy's effects change over time. Observations of distant supernovae, galaxy clustering, and gravitational lensing at different redshifts can constrain how dark energy's density evolves. So far, observations are consistent with a cosmological constant, but more data could reveal evolution. The fate of the universe depends critically on dark energy's nature. If it's a cosmological constant, the universe will expand forever, gradually emptying as galaxies recede beyond each other's horizons. If dark energy's density increases, we might face a big rip. If it decreases, gravity might eventually halt expansion. Each possible future is strange in its own way. The heat-death future is one of increasing isolation and darkness. Galaxies become island universes, alone in an expanding void. Stars exhaust their fuel, black holes evaporate, the universe approaches maximum entropy and thermal equilibrium. In this scenario, the far future is cold, dark, and empty. But it takes an incomprehensibly long time to reach this state. For trillions of years, red dwarf stars will continue burning. For tens or hundreds of trillions of years, white dwarfs will cool slowly, providing faint light and heat. Intelligent civilizations, if any survive that long, would need to adapt. Energy would become precious. Stars would be husbanded carefully. Eventually, civilizations might orbit black holes, extracting energy from matter falling in, sustaining themselves on the last available energy sources. The universe's timeline stretches far beyond its current age. We're living in the stelliferous era when stars dominate the universe's light. This era began about 100 million years after the Big Bang and will last for perhaps 100 trillion years. Most of cosmic history lies ahead, not behind. After the stelliferous era comes the degenerate era, dominated by white dwarfs, neutron stars and black holes. This lasts from about 10 trillion years to perhaps 10 to the 37 years. Most objects are stellar remnants, slowly cooling or accreting material. Following that is the black hole era, from 10 to the 37 to 10 to the 100 years. Black holes are the dominant massive objects, slowly evaporating through Hawking radiation. Even supermassive black holes eventually disappear, though it takes unimaginable time. Finally, the dark era from 10 to the 100 years onward. Only fundamental particles remain, scattered across an unimaginably vast and cold universe. No structures, no complexity, just photons, neutrinos, and electrons with wavelengths longer than galaxy clusters, existing in a space approaching absolute zero. This timeline is speculative and based on current understanding. New physics could change the story. Proton decay, if it occurs, would eliminate ordinary matter much sooner. Phase transitions in the vacuum could alter the universe's properties. Unknown processes might dominate on these extreme timescales. But based on what we know now, this is the universe's future. A long, slow decline from complexity to simplicity, from structure to uniformity, from light to darkness. It's not a dramatic ending, but a gentle fade. There's something poignant about this fate. The universe began in a brilliant flash, a moment of infinite density and energy. It expanded and cooled, forming structure, stars, galaxies, planets. For a brief cosmic moment, it was complex and interesting, and then the complexity fades, not destroyed but diluted, spread across ever-increasing space until nothing interesting remains. We exist in the universe's brief moment of complexity. The past 13.8 billion years have seen structure form and evolve. The next perhaps 100 trillion years will see structure persist and slowly fade. After that, over timescales that dwarf the current age by factors of billions upon billions, the universe becomes simple again. In the grand scheme of cosmic history, galaxies are temporary. They form, evolve, and eventually disperse or fade. The Milky Way will merge with Andromeda, forming a larger galaxy that will eventually exhaust its gas and become quiescent. Trillions of years from now, even this merged galaxy will be a collection of stellar remnants, dark and cold. But for now, galaxies are brilliant. They're the universe's primary structures, the ecosystems in which stars form and planets arise. They're diverse, from small dwarfs to giant ellipticals, from active star formers to quiescent red ellipticals. Each tells a story of formation and evolution. Looking at images from telescopes, seeing thousands of galaxies in a single deep field, each a collection of billions of stars, each potentially hosting billions of planets, the scale becomes overwhelming. Every point of light is an entire galaxy. Every galaxy has a history, a structure, a future. The Hubble Deep Field and its successors show us galaxies at various distances, various ages. Nearby galaxies are evolved, mature. Distant galaxies are younger, smaller, more irregular. We're seeing cosmic evolution played out across space, which is also across time due to light's finite speed. The James Webb Space Telescope pushes this even further, detecting galaxies at redshifts greater than 10, corresponding to when the universe was less than 500 million years old. These early galaxies are laboratories for understanding structure formation, star formation in pristine gas, the formation of the first black holes. Each new observation refines our understanding. Each deep field reveals fainter, more distant galaxies. Each spectrum tells us about composition, motion, age. Slowly, patiently, we're mapping the universe's history and structure, and we're finding that galaxies are not isolated. They exist in a cosmic web, connected by filaments of dark matter and gas. They influence each other through gravity, through tidal forces, through mergers. The universe is an interconnected whole, not a collection of independent objects. This interconnection extends to the smallest scales. The atoms in your body were created in stars, perhaps in multiple stars across generations. Those stars existed in galaxies that merged and evolved over billions of years. The matter you're made of has a cosmic history stretching back to the Big Bang. You're not separate from the universe. You're composed of it, shaped by it, fundamentally part of it. The calcium in your bones was created in supernovae. The iron in your blood was forged in the cores of massive stars. The oxygen you breathe was produced by stellar fusion and distributed by stellar winds. Every breath connects you to stars that died billions of years ago. Every heartbeat is powered by energy from fusion reactions in the Sun, which is itself a third-generation star formed from gas enriched by previous stellar generations. You exist because galaxies formed, because stars created heavy elements, because those elements assembled into planets and eventually into life. This is the cosmic perspective. Understanding your connection to the universe, recognizing that you're not an observer, separate from what you observe but a participant, a part of the cosmic web made temporarily aware of itself. From this perspective, the vast scales and long time scales of cosmology become less alienating. Yes, the universe is incomprehensibly large. Yes, it will exist long after you're gone, but you're part of it. You're the universe experiencing itself, asking questions about its own nature. The fact that the universe can be understood, that patterns emerge from observations, that mathematics describes reality, this is perhaps the deepest mystery. Why should the universe be comprehensible? Why should simple laws govern complex phenomena? Why should we, products of cosmic evolution, be capable of understanding that evolution? These questions may not have answers, or the answers may require perspectives we haven't yet developed. But the questions themselves are worth asking. They reveal something profound about the relationship between mind and matter, between observer and observed. We're standing on a small planet orbiting an average star in an ordinary galaxy, one of hundreds of billions in the observable universe. From this position, using instruments that extend our senses across the electromagnetic spectrum, we've mapped the cosmos on its larger scales. We've discovered that the universe is expanding, that it began in a Big Bang, that it contains dark matter and dark energy. We've traced the evolution of structure from tiny density fluctuations to the cosmic web. We've observed galaxies forming, merging, and evolving over cosmic time. This knowledge is recent. A century ago, we thought the Milky Way was the entire universe. 90 years ago, we discovered cosmic expansion. 70 years ago, we detected the cosmic microwave background. 25 years ago, we discovered dark energy. Our understanding has revolutionized repeatedly within living memory, and it will likely revolutionize again. There are questions we cannot yet answer. The nature of dark matter and dark energy, the details of galaxy formation and evolution, the ultimate fate of the universe, whether the Big Bang was a beginning or a transition, whether our universe is unique or one of many. Future observations will address some of these questions. New instruments will extend our reach. New theories will explain anomalies. The process continues, knowledge expanding as our capabilities grow. But some questions might be fundamentally unanswerable. If the universe is infinite, we cannot observe all of it. If there are other universes, we might never detect them. If the laws of physics themselves emerge from some deeper structure, we might not be able to access that structure. This possibility of fundamental limits to knowledge is sobering. We might be asking questions that no amount of observation or reasoning can answer. We might have reached or be approaching the boundaries of what finite beings in a finite time can know. But even if there are limits, we haven't reached them yet. There's still much to discover, much to understand. Each generation of astronomers has pushed further, seen deeper, understood more. There's no reason to think we've reached the end of discovery. The universe remains full of mysteries. Galaxies challenge our understanding. Dark matter eludes detection. Dark energy defies explanation. Black holes hide singularities behind event horizons. Quantum mechanics and gravity resist unification. These mysteries are not failures, they're opportunities. They're indications that we don't yet understand everything, that there's more to learn, that the universe still has secrets to reveal. And so we continue observing, measuring, theorizing, building larger telescopes, designing more sensitive detectors, developing better models. Each small advance contributes to the larger picture. Each observation constrains the possibilities. Each theory suggests new tests. This is science at its finest. Not claiming certainty but pursuing understanding. Not pretending to know everything but honestly admitting what we don't know. Not being satisfied with mystery but working patiently to illuminate it. The cosmos rewards this patience. It reveals itself slowly, layer by layer, pattern by pattern. What seemed random becomes ordered. What seemed complex becomes, if not simple, at least comprehensible. And with each new understanding, new questions emerge. Looking up at the night sky, you're seeing the same stars ancient peoples saw, the same constellations, the same Milky Way stretching across the darkness. But you understand what you're seeing differently. You know the stars are not fixed to a celestial sphere but scattered across vast distances. You know the Milky Way is a galaxy seen edge on from within. You know that beyond the visible stars are billions more, and beyond our galaxy are hundreds of billions of others stretching to the edge of the observable universe and likely beyond. This knowledge transforms observation. A simple glance at the night sky becomes a view across cosmic distances and times. The light entering your eyes left those stars years or centuries ago. You're seeing the past, observing history written in photons. And in understanding this, you connect to something larger than yourself. You're part of a species that has learned to read the sky, to decode the light, to understand the cosmos. This is a collective achievement, built over generations, the work of countless minds working toward common understanding. The galaxies will continue their slow dance, merging and evolving according to the laws of gravity and dark matter. Stars will continue forming and dying, enriching the universe with heavy elements. The cosmic web will persist, filaments and voids stretching across space. And through it all, on at least one small planet, matter has organized itself into forms capable of observing and understanding. We look out at the universe and see not chaos but pattern, not randomness but order, not meaninglessness but comprehensibility. This is the gift of cosmology. Not just knowledge of what exists beyond Earth, but perspective on our place within it. We are small, yes, but we are part of something vast. We are brief, yes, but we are connected to something ancient. We are ordinary matter, yes, but we are matter that has become aware. In the end, that might be the universe's greatest achievement. Not the formation of galaxies or the creation of elements or the generation of black holes, profound as those are, but the emergence of consciousness, of matter capable of understanding matter, of the universe becoming aware of itself. We are that awareness, brief, limited, but genuine. And for as long as we persist, we will continue looking outward, asking questions, seeking understanding. Because that's what conscious matter does. It observes, it wonders, it seeks to comprehend. The universe provided that opportunity. Through 13.8 billion years of expansion and evolution, through the formation of galaxies and stars, through the creation and dispersal of elements, through the assembly of planets and the emergence of life, the universe has produced observers. And now those observers look back at the universe that created them and work to understand it. This is perhaps the most profound relationship that exists, the universe and consciousness, matter and mind, cosmos and comprehension. The journey continues, the questions remain, the mystery persist. But we persist too, asking, observing, understanding. Small parts of a vast whole, working to comprehend that whole. Temporary expressions of eternal principles seeking to grasp those principles. This is what it means to study the cosmos, to connect with something larger, to participate in the universe's self-discovery, to be, for a brief moment in cosmic time, the means by which the universe comes to know itself.